Today, geometry, lesson 7, using inductive reasoning. All right, so your essay question is going to be, how is inductive reasoning used in the real world? The real world, I want to be clear on these essay questions, the real world is not school, okay? We're talking about outside of these walls, how is this used? Okay, how can it be used? And I don't mean, again, like I've kind of addressed before, words like construction, right? Those are words, but you're not telling me anything. Okay? I want to know how, why, where, those types of things. Give me specifics. Okay, so we're going to talk about inductive reasoning. Inductive reasoning is the process of reasoning that a rule or statement is true because several specific cases are true. Okay? Can anybody, I mean, just that sentence alone ought to give you some ideas. Go outside of the world of math, right? When is inductive reasoning used? The process of reasoning that something is true because several other specific cases of it are true. That's exactly what I was thinking. A court of law, right? They use what they call precedent, right? That, you know, there's a precedent for this, and because this case has been gone to trial and it's exactly like this, and it was ruled this way, okay? This process of reasoning that something is true because several other specific cases are true. Inductive reasoning can be used to formulate a conjecture about something. A conjecture is a statement that is believed to be true. Okay, so something that we believe. All right, if a conjecture can be proven, it becomes a theorem. Okay, but really, in all reality, another word for theorem, we use another word that sounds a lot like theorem. What's another word that sounds a lot like theorem? Theory. Where do we deal in theories at? Science. Okay, there are scientific theories based upon conjectures, things that are believed to be true. Okay? Now, if a conjecture can be proven, it becomes a theory, but a theory is still not a fact. Okay? If there's evidence to support it, it becomes a theory, but it's still not a fact. Instead of formulating a conjecture by looking at data, sometimes it's necessary to test a conjecture using given data. Sometimes you can't tell if something is true per se. For instance, there are statements that are really hard to prove. One statement that I can make is, all roses have thorns. Okay? There's a statement. Now, what would we have to do to prove that statement? At what? How many? All of them. Is that going to be possible? No, it's going to be impossible to check all roses. Okay? But what we can come up with to prove that statement false is to come up with a counterexample. And if I can find a counterexample, then I don't need to look at every single rose in the world. I just need to find a rose that what? Doesn't have thorns. Okay? So even if even one example can be found that does not support the conjecture, then the conjecture is incorrect. An example that does not support the conjecture is called a counterexample. Okay, now I'm going to be specific about counterexamples here, and this isn't necessarily something that's on the board, so you have to listen closely. There are rules to a counterexample. Okay, for instance, let's go with my original statement. All roses have thorns. Okay, and we want a counterexample. The first thing that I have to have is a rose. Okay, that's the hypothesis. My hypothesis is that we're talking about roses. Is it going to do me any good to pull in a dandelion and say, here, look, it doesn't have thorns? Is that a counterexample? If I find a lily or a daffodil, right, are those counterexamples? No, I have to have a rose. The next thing is that it has to not have thorns. Okay? So when we're talking about statements, we're talking about something that has a hypothesis, if, and a then, which is a conclusion. Okay? A counterexample will meet the hypothesis but it will prove the conclusion is wrong. One of my examples that I've used over the years, just because we're here at Milan and there's always been this rivalry slash hatred of Putnam County. So this is a statement. Let's see. All guys from Putnam County are good looking. Okay? So to prove that statement false, what do I have to have? Okay? Let's, instead of just, kind of having that kind of remark, let's kind of follow through here. What do I have to have? I got to have a Putnam County, so he can't be from Knox County, right? Can't be from Schuyler County, right? He's got to be from Putnam County. What else? What's that? No, not according to this. Okay? Can it be a girl? No, because what was the statement? If a guy is from Putnam County, then he's good looking, right? So it's got to be a guy, and he's got to be from Putnam County. What else do I need to have a counterexample? I got to find a butt ugly Putnam County guy, right? His name is Daryl, right? And we can bring him in here and say, here's Daryl. Looks like he's been beat with a football bat, right? Looks like he fell out of an ugly tree and hit every branch on the way down, right? Okay? He's my counterexample. Right? But he has to fit the hypothesis. He has to be a guy from Putnam County, but he's got to be ugly. Okay? And by Jordan's admission that he's looked at all of them, and none of them are good looking. Okay. So you learn more about counterexamples in lessons 10 and 14, which is where we get into some of that information at. Okay? This is our last slide here before we actually try to answer some questions, get you out of here. So even though conjectures are not proven, scientists often use conjectures to describe real-world phenomena. These conjectures are carefully studied and tested, but often difficult to prove them formally, beyond a shadow of a doubt. Okay? So what I don't want to see in your statement or in your answer to the essay question is scientists or science. Okay? That's not an acceptable answer, right? You have to be specific. What in science? Okay? What specific theory? Okay? Give me an instance. Give me, science covers such a broad realm and spectrum that I'm going to end up giving you a 0 if you say science or scientists. That's still great. What about them? What about a biologist has to do with inductive reasoning? The question would be then, how does a biologist use inductive reasoning? And why? Okay. So a better sentence would be, scientists use the scientific method to test their hypothesis to see if their conjecture might make a good theory. Okay, that would be something that you could write, and that would be a good sentence. Okay, I'm trying to get you guys, yes, part of our stuff this year is that we're trying to get you guys to work on being better writers. But from my side of things, as a math teacher, I want you to actually think, not just, how do I answer this question, on a homework assignment, or how do I answer this question on a test. I want you to think about applications. Okay? How can things that I'm learning now be applied? Where can I use this potentially? Okay? All right, we'll stop right there. Actually, let's look at question. Okay? All right, here's question number 1. Complete the conjecture. The sum of two odd numbers is what? What do you think? Heard somebody say even? All right. Can we find a counterexample to that? No, we can't. So he's right. The sum of two odd numbers is even. All right, number 2, we've got a table. It says make a table that shows the number of squares in each figure, then tell how many squares are in the 5th figure of the pattern. So let's go ahead and let's do that up here. All right, we got X and Y, we got inputs, outputs. My inputs are my figure numbers. So figure 1, figure 2, figure 3, figure 4, and figure 5. Now they only go to figure 3. How many boxes are in figure 1? Jose? 1, okay. All right, how many boxes are in figure 2? Jose? 3. Okay, Katie, how many boxes are in figure 3? 6. All right. How many boxes do you think are going to be in figure 4? We think 9. Okay. Let's see. So in figure 4, we'd have 1, 2, 3, 4, 5, 6. But how many would we have along the bottom? 4. What's 6 plus 4? 10. So were you correct? No. You saw 1, 3, 6, but you were really looking at 3, 6, 9, right? But, okay, so we went 1, 3, 6, 10. What do we think is going to be in figure 5? If there's going to be 4 along bottom, along 15, okay, we're going to have 5 along the bottom. So let's kind of look at this. From 1 to 3, how many did I add? I added 2. Okay. From 3 to 6, how many did I add? 3. Okay. From 6 to 10, how many did I add? So do we see the pattern? Okay. All right. That's my pattern. All right. So 15. And of course, we should find an answer in here that's going to match that. Does A match it? Okay. Figure 5 has 15 squares. Okay, good. All right. Let's kind of scroll down here a little bit and see if we can find another one. Okay. This is a question that has shown up on some tests. Make a table of values for the rule x squared minus 16x plus 64, wherein x is an integer from 1 to 6. Okay, so x is an integer from 1 to 6. 1, 2, 3, 4, 5, 6. You're going to need your calculators for this. All right, because what we're going to do is we're going to plug in 1 for x in each of those spots and see what we get. Okay, so for our first one, we should have, 1 squared minus 16 times 1 plus 64. Okay, Michael tells me I got 49. Okay, then I'm going to go through and I'm going to do that same thing with 2. If you're not using a do you not have one, Katie? Okay, why don't you grab one from over here. What'd you get, Chandler? 36 is correct. Why did you think it was wrong? Ah, okay. Yeah, but look at what you're doing here. Negative 16 times 2 is going to give you a bigger negative number there, right? Okay. So then I'm going to do 3 squared minus 16 times 3 plus 64. Jordan, tell me what you get. 32 is wrong. Yep. Jordan, type it in there. Tell me what you get. Nope. This right here, I'm just telling you to type it in exactly how I've got it written up there. You're not even having to figure it out. $25 is correct. All right, now I'm going to help you out. All right, the next one's going to be 16. The one after that is 9. This one is 4. You know how I was able to do that? How was I able to do that? Well, it does help to be a math teacher. But what you should recognize by the time you get here is you should see a pattern, correct? What pattern do you see, Katie? What's that? Nope, not subtracting 7. What do you notice anything about 49, 36, 25, 16, 9, and 4? What does anything true about those numbers? They're perfect squares. And so what we have is a descending value of perfect squares, right? All right. So if I went to 7, does anybody know what I would get? 1, right? Because 7 squared is 49, 6 squared is 36, 5 squared is 25, 4 squared is 16, 3 squared is 9, 2 squared is 4, which means 1 squared is 1. What should 8 be? 0. Okay? But what about, and this one I want you to plug in, what about 9? 9 squared minus 16 times 9 plus 64. What do you get? You got 1 again? Katie got 1. You're wrong, by the way. Got 1? Did you get 1 that time? No, you need to try it again. What did you get? 1. Okay, so 1. So what we see is the pattern appears to be a decreasing set of perfect squares. Can anybody tell me what the counterexample is? No? How about x equals 9? Why is x equals 9 a counterexample to the statement that the pattern is a decreasing set of perfect squares? Right, it's no longer going down. By the time I get to 0 and then I do 9, now I'm going back up. Okay? So likely if I did 10, I should probably get 4. Okay? 11, 9, 12, 16. See what I'm saying? It'll go back around. Does that make sense? Okay. All right, so A is our answer. You might see that question on the test, but you'd have to know how to actually prove it, how to show it. All right, I'm going to stop right there and let you guys work, and I do expect you to work and not be on cool math games.